This is lesson 2.4, solving mixture and uniform motion applications. Our learning objectives are to solve coin word problems, solve ticket and stamp word problems, solve mixture word problems, and solve uniform motion applications. This is the grand finale of our chapter 1 and 2 content. And I want to remind you of our 7-step process of how to solve word problems that we discussed in our last lesson. So step 1 is read the problem. Make sure all the words and ideas are understood. Step 2, identify what you were looking for. Step 3, name what you were looking for. Choose a variable to represent that quantity. Step 4, translate that into an equation. Step 5, solve the equation using good algebra techniques. Step 6, check the answer in the problem and make sure it makes sense. And step 7, answer the question with a complete sentence. We'll generally go through these 7 steps as we work through all of the word problems we have today. So let's start with a section on solving coin word problems. Now, in each example that I give you today, I create a table. So here's a table, and you will be responsible to create a table from scratch when you receive a problem like this on the test, if this is how you choose to organize your information and solve. I highly recommend it. All right, so example 2.39. Well, first let's talk about the total value of coins definition up above it. So the total value of coins, for the same type of coin, the total value of a number of coins is found by using this model. The number of coins times the value of the coin type equals the total value. So for example, if I have 10 coins and they're valued as quarters, well, the value of each coin would be 0.25 because quarters are worth 25 cents. Now, we're going to multiply 10 times 0.25 to find the total value, which is $2.50. All right, so that's the total value of 10 quarters. Now that we have that basic idea down, let's go ahead and look at example 2.39. Jesse has $3.02 worth of pennies and nickels in his piggy bank. The number of nickels is 3 more than 8 times the number of pennies. How many nickels and how many pennies does Jesse have? Well, let's begin by organizing our information. We've got pennies and we've got nickels. So I'm going to write those as the types of coins that we're dealing with. Now, we don't know the number of pennies or nickels. So let's call the number of pennies P. And then the number of nickels was told to us in terms of pennies up above, right? The number of nickels is 3 more than 8 times the number of pennies. So I can create an expression like that says 8 times P plus 3. All right, so we've written an expression for the nickels in relation to the pennies. Now we know a penny's value is 1 cent or $0.01, and a nickel's value is 5 cents or $0.05. Now, what we're going to do to find the total value is multiply the number by the value. So 0.01 times P is, so we'll multiply the row together, right? So we have 0.01 times P. Now the next row, the second row, we'll multiply that stuff together, like 0.05 times 8P plus 3. And now we know that our total value is $3.02. It was given to us in the problem. So we're going to have $3.02 as our total value. Now what's great about creating this column, well, all of this table, is this specific column right here can be added and set equal to create an equation. Let's write the equation down below. It's 0.01 times P plus 0.05 times 8P plus 3 equals 3.02. Now that I've created an equation, I can now solve that equation for P, which will tell me the amount of pennies that Jesse has. So let's jump in a little bit, and you might notice we have some algebra to do. We've got to distribute. And so rewriting this equation, I have 0.01 times P plus, well, 0.05 times 8P, which is 0.40P, plus 0.05 times 3, which is 0.15, and that equals 3.02. Let's combine like terms. So 0.01p plus 0.40p is 0.41p. Okay, so we get 0.41p. And then the constants we want to move to the other side. So I'm going to subtract 0.15 from left to right. And $3.02 minus 15 cents is $2.87. Next, to finish solving for p, I'm going to divide 0.41 to the other side of the equation. So the amount of pennies that we have ends up being 7, right? 2.87 divided by 0.41. That gives me 7, which we've got to have an integer value at this point, right? Like the number of pennies has to be a whole number. And so it looks safe. We found a whole number for the amount of pennies. Well, we know how many pennies Jesse has now. He has 7 pennies. But now we need to find the amount of nickels. But what's great is we already have an expression for the amount of nickels that we stated above. It was 8p plus 3. Okay, so I can plug 7 in for p. So the amount of nickels will equal 8 times p, which is 7, plus 3. And 8 times 7, well, that gives us 56 plus 3, that's 59. Okay, so we have found the amount of nickels and the amount of pennies. We might as well write a statement like Jesse has 7 pennies and 59 nickels. All right, we have gone through the full solution process for this problem. Now, you might go back. Remember, we're following this 7-step process as we go through this information. Okay, and looking back, you'll see that I've done all of that. So besides coin word problems, what other kind of word problems will we encounter? Well, we also have ticket and stamp word problems. Let's begin with stamps. So, stamps, like when you mail something in the mail, they have value, right? 49-cent stamps versus 35-cent stamps. Let's look at example 2.40. Danny paid $15.75 for stamps. The number of 49-cent stamps was 5 less than 3 times the number of 35-cent stamps. How many 49-cent stamps and how many 35-cent stamps did Danny buy? Great. So let's organize this information into the same type of table. Now, we've got 49-cent stamps and 39-cent stamps, right? So I'm going to put that. Great. So these are the types of stamps, 49 cents and 35 cents. Now, looking deeper, I'm going to highlight this sentence right here because it compares the type of stamps with each other. So the number of 49-cent stamps was 5 less than 3 times the number of 35-cent stamps. So if I call the 35-cent stamps X, I'm going to use that as the variable number of them. Then the 49-cent stamps was 5 less than 3 times that. So I have 3 times X minus 5. All right, we've written expressions to represent the number of these types of stamps. Now, their value, well, a 49-cent stamp is valued at 0.49. Okay, and then a 35-cent stamp, well, its value would be 0.35. Now, let's multiply the number times the value in each row and column. So I've got to multiply 3x minus 5 times 0.49. A better way to write it would be 0.49 in front, and then in parentheses, we'll have the 3x minus 5. Okay, now looking at the 35-cent stamps number times value, we get a 0.35 times x. And we know that the total will equal $15.75, the grand total value. So we're going to write that in this row below. Now this column right here creates an equation where we sum up the total value for each type of stamp and set it equal to the total value, and that gives us an equation that we can solve for x. I'm going to write the equation below. 0.49 times 3x minus 5 plus 0.35 times x equals 15.75. Well, let's solve this equation. So we're using some algebra skills. We're distributing first. 0.49 times 3x gives me 1.47x. All right, and then 0.49 times negative 5 gives me negative 2.45. Now I have the addition of the 0.35x, and that equals 1575 still. There are like terms that we can combine together, and we want to move the constants all to one side. So I'm going to add this 2.45 from left to right. And combining 1.47x with 0.35x gives me 1.82x. 1575 plus 245 is $18.20. And to finish solving for x, we're going to divide 1.82 from left to right. Great. So x is equal to 10. Okay, we have solved for x. Well, we have to go back and say, what did x represent? X represented, well, the 35-cent stamp, because that's what we set equal to x, right, for the number of 35-cent stamps. So I've just found there are 10 35-cent stamps. Now I can go up here and I can replace this x with 10 to figure out how many 49-cent stamps there are. So let's do that. So if we took 3x minus 5, the expression for 49-cent stamps, and we replaced x with 10, we'd have 3 times 10, which is 30, minus 5, which is 25. Now, let's keep things always organized, and we're going to write a concluding statement like Danny has well 10 35-cent stamps and 25 49-cent stamps. Okay, so we just gave context to the solutions that we found for this real world application. Okay, so there we go. Let's now move on from talking about stamps to talking about tickets. So example 2.41 discusses whale watching tickets. A whale watching ship had 40 paying passengers on board. The total revenue collected from tickets was $1,196. Full fare passengers paid $32 each and reduced fare passengers paid $26 each. How many full fare passengers and how many reduced fare passengers were there on the ship? Great. Let's organize all of this information in our table. Once again, I'm creating these tables so that you can start to organize the information, but you'll have to be the one that creates the table from scratch when you test. So we're dealing with two different types of fares, like the full fare and the reduced fare. All right, so I'm just writing that here. And now, what is the number? Well, those are the things we don't know, right? We're trying to find out how many full fare and reduced fare passengers there were on the ship. So we know that there were 40 paying customers total. So if we're dealing with, let's call the full fare F, the reduced fare amount would be 40 minus F, because the total for the full fare and the reduced fare have to add up to 40. So if full fare is F, take 40 and subtract off F and you get the reduced fare. Now, what is the value for each fare? Well, the full passengers paid $32, so I'm going to put 32 for full fare. And the reduced fare passengers only paid $26, so I'll put 26 here. Now let's multiply the rows together, like the number F times 32 will give me the total value here, and 40 minus F times 26 gives me the total value here. So I end up with 32 times F and 26 times 40 minus F. And the grand total that everything should equal is $1,196. So the total value, the grand total, goes in the very bottom here. Okay, there we go. Now, just like before, we're going to take this information in this column for the total value, add the pieces together, and set equal to the grand total. So let's write the equation down below so that we can use some algebra to solve it. 32F plus 26 times 40 minus F. That has to equal 1,196. Now let's distribute. And we find 32F plus, well, 26 times 40 is 1,040. And then that's minus 26F equals 1,196. Now let's combine like terms, and we'll take the constant and subtract it to the other side. And 32F minus 26F gives me 6F. And that equals 1,196 minus 1,040, which gives me 156. I'll now divide by 6, and I've solved for F. F equals 26. Well, let's recall, what did F represent? Well, that's the number of full fare tickets, right, that were sold. Now, how do I find the number of reduced fare tickets? Well, I take 40 minus F because there were 40 passengers total. So if I take the 40 total passengers and subtract off the full fare passengers, that'll tell me the reduced fare passengers. So I'll do it right here, 40 minus 26, and that gives me 14. Great. So we have our answers. Now's a great time to write a statement so that we show clearly how many of each we have. So I'll say there are 26 full fare tickets, or full fare, we'll just put ticks for tickets, and 14 reduced fare tickets. Great. We have now solved this real world application. All right. So you'll see that the three problems we've done so far today about coin word problems, stamps, and tickets are all set up in the exact same way to solve. Let's now look, and we're going to kind of change gears to mixture word problems. Okay, so you'll notice the table that we set up is very similar, but there are some differences. To find a mixture, we would take the number of pounds of something and multiply by its value to know its total value. It's incredibly similar. As we start doing this, it'll make sense. So Jacob is mixing raisins and nuts to make 25 pounds of trail mix. Raisins cost $4.50 a pound, and nuts cost $8 a pound. If Jacob wants his cost for the trail mix to be $6.60 a pound, how many pounds of raisins and how many pounds of nuts should he use? Let's begin with the type. So what are we mixing together? Well, we've got raisins and we've got nuts. And then when we combine them together, they result in the trail mix. So I'll put trail mix in the third row of this column. Next, well, we have to know how many pounds of raisins and how many pounds of nuts he should use. But there's going to be 25 pounds total of trail mix. This is important. So we know the trail mix number of pounds will be 25. So the amount of raisins, let's call it X. Or you could use R for raisins if you want to. But we'll just generally use X. And then the nuts, well, that would be the total pounds of trail mix minus the pounds of raisins. Because all we have is raisins and nuts for this trail mix. So we would take the 25 grand total and subtract off the amount of pounds of raisins, and that would give us the pounds of nuts. Now, we know the value for the raisins and nuts. For example, the raisins cost $4.50 a pound, and the nuts cost $8 a pound. And the trail mix is going to cost $6.60 per pound. Now, just like before, we'll take the number of pounds and the value for each row and set it and multiplying it together make the total value. So x times 4.50, right? I could just write it as 4.50 times x. And then 8 times 25 minus x. And then, well, 660 times 25. And if I add this column together, setting it equal to the grand total value, I have an equation that I can solve for x. So let's write that equation below. I've got 450 times x, right? 4.50 times x, plus 8 times 25 minus x equals 6.60 times 25. We're going to distribute, and we're going to get the variable by itself in this linear equation. So cleaning this up, we get 4.5x. We can drop the 0 to make life easier if we want to, plus 8 times 25, which is 200, minus 8 times x equals, well, 25 times 660, 6.60 is 165. Now, I'll subtract the constant from the left-hand side to the right-hand side, and I'll combine like terms with the variable x. 4.5x minus 8x is negative 3.5x. And 165 minus 200 is negative 35. At this point, I'll divide by negative 3.5. And I find out that x is equal to 10. X is equal to 10. Negative 35 divided by negative 3.5 is 10. Well, what have I just found? I have just found the number of pounds of raisins. Right, let's look back. We called the number of pounds of raisins x, and we just found that. There are 10 pounds of raisins. To find the amount of nuts, we just take 25 minus x, which we now know is 10. 25 minus 10 gives us 15. It's time to write a concluding statement like, well, Jacob should use $10 pounds of raisins and 15 pounds of nuts. Great. We have now solved a mixture problem with trail mix. Well, we're ready to move on to solving uniform applications, uniform motion applications, and that'll take up the rest of this lesson, but there are a variety of examples where things slightly change, okay? So what is uniform motion? Uniform motion is simply distance equals rate times time. So if I'm going the same speed for a certain amount of time, then that will tell me my distance. For example, think about driving in a car. Like the total distance that you travel is equal to the rate that you're going. Let's say I'm going 50 miles per hour multiplied by the amount of hours. Let's say I do that for 3 hours. Well, 50 miles per hour times 3 hours would tell me, well, I'm traveling a total distance of 150 miles. All right, so this is true as long as I'm going generally an average same pace, right? Same rate of 50 miles per hour the whole time. Okay, so distance equals rate times time. Oftentimes we abbreviate this to d equals r times t. D, distance, equals r, rate, times t, time. And time is generally in hours. Okay, so usually we're thinking in terms of hours, and then we could be thinking in terms of our rate, in distance, in miles or kilometers or feet. It just depends on the scenario that we're talking about. One tip for you as we proceed is to, if you struggle, to draw a diagram that illustrates what's happening. Okay? So that's a good strategy as you proceed. Well, let's jump into example 2.43. Wayne and Dennis like to ride the bike path from Riverside Park to the beach. Dennis's speed is 7 miles per hour faster than Wayne's speed, so it takes Wayne 2 hours to ride to the beach while it takes Dennis 1.5 hours for the ride. Find the speed of both bikers. So I've once again included a table, and you'll see how this table is slightly different where I have a rate column, a time column, and a distance column, and rate times time equals distance. Now let's write down who we're talking about for each row. First of all, we're dealing with Wayne and Dennis. Well, we don't know the speed of the bikers. Speed is the same thing as rate. Okay, so we don't know the rate. So let's call Wayne's rate R. But what we do know is that Dennis is going 7 miles per hour faster than Wayne. So if we called Wayne's rate R, Dennis would be the same rate plus 7. So R plus 7. Now, we see that it takes Wayne 2 hours to ride to the beach. So the amount of time for Wayne is 2. And it takes Dennis 1.5 hours for the same ride. So 1.5. Great. Now, they're both riding the same pathway. So they're both going the exact same distance, but they're going at different speeds and for a different amount of time. In the end, their distances are going to be equal to each other. All right, so, well, for Wayne, if we multiply rate times time, we would have 2 times R. And for Dennis, we'd have 1.5 times R plus 7. Now, since they are traveling the same distance, we can set these two pieces equal to each other, right? Their distances are equal. So we're going to set these two pieces equal, and we don't have to worry about this bottom column in this circumstance. So let's take 2R and set it equal to 1.5 times R plus 7. Now, all we have to do is solve. We've set everything up, and so we'll distribute, and we'll find 2R equals 1.5R plus, well, 1.5 times 7 gives 10.5. Now, the goal is to get all the terms with the variable on one side of the equation. So I'm going to subtract 1.5 times R from right to left. And so now my new equation, 2R minus 1.5R, gives me 0.5R, which is equal to 10.5. And now to finish, I'll divide by 0.5 from left to right. I've gotten R by itself, and it's equal to 10.5 divided by 0.5, which is 21. Well, let's think for a second. What did we just find? Well, we just found R, which is Wayne's speed, his rate. Okay, so it seems like Wayne was going 21 miles per hour. Now to find Dennis, we would take the 21 miles per hour we just found to find Dennis's rate, and we'd add 7 to it. So I'll do that down below and say 21 plus 7, well, that equals 28. So let's write a concluding statement like Wayne's speed is 21 miles per hour, and Dennis's speed is 28 miles per hour. All right, we've just clarified that we know exactly which person was going what speed, making it very clear for whoever is reading the conclusion to our problem. All right, so let's move forward with more uniform motion applications. Here's example 2.44. Karina is driving from her home in Anaheim to Berkeley on the same day her brother is driving from Berkeley to Anaheim. So they decide to meet for lunch along the way in Buttonwillow. The distance from Anaheim to Berkeley is 395 miles. It takes Karina 3 hours to get to Buttonwillow, while her brother drives 4 hours to get there. Karina's average speed is 15 miles per hour faster than her brother's average speed. Find Karina's and her brother's average speed. Well, creating a table might look like this. I've got Karina and I've got her brother. So we'll just call her brother. Okay. Now we see something important about the rate that they're going. Karina's average speed is 15 miles per hour faster than her brother's average speed. So if her brother's average speed is x, then Karina's would be x plus 15. I've been told the time that both of them are traveling. For example, Karina is traveling for 3 hours. So I'll put time as 3. And her brother is driving for 4 hours. So I'm going to put time as 4 for her brother. Let's multiply the rate times the time, and we'll make it look really nice for the distance. So the distance for Karina would be 3 times x plus 15. And the distance for her brother would be 4 times x. And in this case, I was told the total distance between Anaheim and Berkeley. So I know the total distance, because they met somewhere in the middle. Well, the total distance would have to be 395. So I've got a column right here that I can use as an equation to solve for x if I simply add the distances for Karina and her brother and set them equal to the grand total distance. All right, let's jump into it. I'm going to write out the equation like 3 times x plus 15 plus 4x equals 395. Now, let's jump into solving it. First, distribute. So we get 3x plus 45 plus 4x equals 395. Next, well, subtract the constant to the other side, so it's with the other constant, and then take the terms with the variable in it, like 3x and 4x, and add them together to make 7x. And 395 minus 45, that gives me 350. And now I'll divide by 7, and I find out x equals, well, x equals 50. Now stop. Now that we've solved, let's think about, well, what does this represent that we just found? We just found x is 50. Well, looking back, well, x is Karina's brother's speed. And if we take that and add 15, we'll find Karina's speed. So let's do that really fast. 50 plus 15 equals 65. Well, let's create a concluding statement now that we know both people's speeds. So Karina's average speed well, it's 65 miles per hour because she was going 15 miles per hour faster than her brother. And her brother's average speed, it was just 50. That's what we originally found. Awesome. We have solved this Uniform motion application. All right, we're going to jump into a couple last examples. They're slightly different than what we've seen so far. So here we go. Example 2.45. Two truck drivers leave a rest area on the interstate at the same time. One truck travels east and the other travels west. The truck traveling west travels at 70 miles per hour, and the truck traveling east has an average speed of 60 miles per hour. How long will they travel before they are 325 miles apart? All right, so let's fill out our known information. Well, there's a truck that's going west. I'll write that one first. Okay. And there's a truck that's going east. And here's a little diagram for us. See, they leave the same rest area at the same time. So here's the rest area, but one of the trucks, see, it's traveling from the rest stop westward, and then one of the trucks from that rest stop is going eastward. And they end up 325 miles apart from each other. Okay, so after they've done their traveling, they are a total distance of 325 miles apart. So it can be useful to draw a diagram of what's happening for your brain to understand. Now, let's look at some key details, like the truck traveling west was going 70 miles per hour. That's a rate. Okay, that's their speed, so I'm going to put 70. And the one going east, they were going slower. They were going 60 miles per hour. Now, the question asks, how long will they be traveling before they're 325 miles apart? So that time is t. And it's that time t for both the trucks because they're traveling for the same amount of time. And let's go ahead and multiply the rows together, like 70 times t, right? And so we write the total distance is the rate times time, which is 70 times t. And then for the truck going east, that would be 60 times t. And we were given a total distance. The total distance that they traveled together is 325 miles. So we can take this equation right here, well, this column, I should say, and turn it into an equation by doing stacked addition and setting it equal to the grand total. So writing an equation out, I would have 70t plus 60t. Well, that's equal to 325. And this is a really easy equation to solve because all the variable terms are on one side and the constant on the other. So 70t plus 60t gives me a 130t. That equals 325. Now all I have to do, I'll do it in red, is divide 130 from left to right. And I find out t is equal to 2.5 hours, 2.5. Okay. Great. So these two trucks are traveling 2.5 hours, 2.5 hours before they are 325 miles apart from each other. This is our concluding statement. Let's finish strong with our last example of this lesson. Example 2.46, when Naoko walks to school, it takes her 30 minutes. If she rides her bike, it takes her 15 minutes. Her speed is 3 miles per hour faster when she rides her bike than when she walks. What is her speed walking and her speed riding her bike? In this problem, you want to be careful because for the initial statements, they're talking about minutes. But when they're talking about the rate, they start talking about hours. All right, so we've got to be very careful as we move forward in setting this up. So if I were you, I would change minutes, the rate, or the amount of time that she's traveling. I would change it to hours. Like 30 minutes is 1/2 of an hour, and 15 minutes is 1/4 of an hour. So you'll see it as I set it up. So we're talking about walking to school versus biking to school. And we don't know the rate. So we know a comparison of the two rates. Like when she's riding her bike, she goes 3 miles per hour faster than when she walks. So I could say walking is the rate R. That's what I don't know. I don't know how fast she's walking. But I do know that biking would be R plus 3 because she'd be going 3 miles per hour faster than her walking speed. Now, I do know the times. When she walks, it takes her 30 minutes, which is 1/2 of an hour. All right, so you could write it as 1/2, or you could write it as 0.5, but let's write the time as hours to help us, because that's how we're thinking about the rates in miles per hour. And when she bikes, well, the amount of time is 1/4 of an hour, so you could write 1/4, or you could write 0.25. So it just depends if you want a fraction or a decimal. I'll put them as decimals just for fun. So I know the total distance walking would be 0.5 times r, right? The rate times the time. And then biking would be 0.25 times r plus 3. And what is the total distance? Well, no matter what, she's traveling the same distance to school, whether it's walking or biking. So we can set these two pieces equal to each other, and we don't need a grand total. Okay, so when you're traveling the same distance, no matter, what scenario you're in, you could take these pieces and simply set them equal to each other. Now, we've got an equation that we can solve. So I'm going to distribute 0.25 into both of these terms. I will rewrite the equation. And 0.25 times 3 is 0.75. There it is. Now I've got to get all the terms with r to the same side of the equation, all the variable terms. So I'll do that. And 0.5r minus 0.25r is 0.25r, and that equals 0.75. Dividing by 0.25 from left to right, I find out that the rate is 3. Okay, so r is 3. Now's a great time to stop and think about, what did we say r was? Well, we said r was Naoko's rate when she's walking. And if I take that same number, which was 3, and I add 3 more, that'll give me her bike speed. All right, so I'm going to do that. I'm going to take r plus 3, which is 3 plus 3, which is 6. Let's write a concluding statement so it's clear to everybody. Naoko's walking speed, see, it's 3 miles per hour. And her biking speed is 6 miles per hour. Great. So we've just looked at a variety of uniform motion applications. And you did a great job following along with me. Thank you. This is the final lesson in preparation for our Chapter 1 and 2 tests. And it's kind of the grand finale, making sure that we understand how to read word problems, turn everything we see into mathematical equations and expressions. I hope that this has been helpful for you as you've looked at me write out and organize the information into tables. And I look forward to working with you as we continue to develop your skills in preparation for your first test. We will be doing a review of the all of the sections up to this point to make sure that you're ready to go. Thank you. Have a great day.